their own point of view as to what an atom looks like. So I bet you a lot of you drew the atom that looks like this. How many of you drew an atom that looks like that? Anybody? Nobody?
I did. That's the one that I assumed that it was.
Yeah. All right. I think a lot of people do see it that way. That's how I see it as. If you've ever watched The Big Bang Theory, that's a good example. All right, they show the atom at the very beginning. How many of you watched Big Bang Theory before?
I do.
Yeah, so they show the atom rotating as in the introduction to the TV show. So this is okay. That's an acceptable model of what an atom looks like, but it's not what the most current model looks like. And that is actually something that we will get into not today, but actually later on down the road in chapters 6, 7, and 8. So now to start, the atom actually comes back to the Greek era, all right? And so the atom actually started with this appearance here. What you see is a billiard ball. A billiard ball is like a pool ball, and or a bowling ball for that matter. You can think of a bowling ball. So the men that are responsible for coming up with the atom that we see today, these are just a few of them. And so we're going to be looking at these guys and talking about what they discovered and how important that was to our understanding of what the atom is. Does anybody know any of these guys, by the way? Anybody know? What about this? What era did this guy come from?
Roman.
Yeah, pretty close. Yeah, exactly. And then these other guys here, well,
Is anybody Rutherford?
one of those, yeah. One of them are.
Thompson.
Yeah.
Is the middle bottom one Nikola Tesla?
It looks like it, don't it? But
Yeah,
it's
it
not.
does.
It's not. All right, so if you look at the timeline, there'll be parentheses at the top of each box. There's a time stamp of when this happened approximately. That's what goes in the parentheses, just so you know. So Democritus is a Greek philosopher, and what did Greek philosophers do best? They asked questions, and then the hardest part was when they asked these questions, they had to then answer the questions, which is not the easy part. That's the hard part because they were lacking the technology. All they had back then were togas and fires. I don't know really exactly how much other stuff because I'm glad I didn't live there. But anyhow, if I lived in that time frame, I'd be what 2,400 years old now. You might call me Methuselah. That was a joke, by the way. I'm not that old. I could be, but no, not really. Half of y'all see me. The other half, you'll see me tomorrow and Thursday, right? So he said, could matter be divided into smaller, smaller pieces forever, or was there a limit to the number of pieces of matter could be divided? And so to answer this question, his theory says that matter could not be divided into smaller, smaller pieces forever. Eventually, the smallest possible piece would be obtained. This piece would be indivisible. Now, that's the important part here, is that he is saying that the atom cannot be divided anymore. Once you get to the smallest part, that's it. So in this case, that smallest part was indivisible. So he named the smallest part of matter Atomos, meaning not to be cut. So Atomos is where the atom originates its name from, but Atomos means that the atom cannot be cut in half. So once you get to the atom, it's a solid particle. You can't break it down any further. It's what it is. So now obviously there's some problems with that. Now, to Democritus, atoms were small, hard particles that were all made of the same material but were different shapes and sizes. Atoms were infinite in number, always moving and capable of joining together. There's some problems with that second bullet point, and it's underlined infinite. Infinite means that there is infinite number of atoms present. So, is that true? Is there an infinite number of gold atoms in the world right now?
Nope.
Right. So there's a lot of problems with that statement. Now, keep in mind that he is trying to describe and explain this theory that he's come up with and the answering the question. And so he's working with just what he can see with his naked eye. Now we have the instrumentation that helps us. His theory was ignored and forgotten for more than 2,000 years. Why? So the answer to that is there were other philosophers at the time, Aristotle, Plato. All right, these were two big names. All right. Do any of y'all know any other philosophers? All right, well, their theory was fire or air, water, and earth. So that you take the four elements, combine them together, and you get your atoms that you see that are present. So obviously that theory is wrong, and it's wrong for a lot of reasons. But back then, since they were the more popular philosophers, people really looked and believed what they said at that point in time. So Democritus was just another person, and nobody really cared about what he says until now. So the timeline basically looks like this. You have the Greek era, then there's a lot of absence between that time period between Democritus and the Daltons model. So Dalton's model we'll get to in just a few minutes. So there's another reason besides the fact that you have Aristotle and Plato. The other reason is religious background. So people did not want to step out of bounds and go against the church because they didn't want to be exiled or executed for their thoughts. And so that's something that really kept this low key until the early 1800s when things started kicking back up. Now, I do want to make a comment that alchemy was something that was popular starting around the 1600s and on up to about 1800. The alchemists, they were trying to take different elements, combine them together to make precious elements like gold and silver. Because if you can make gold out of other elements, then you've got an upper hand on the rest of the world, because now you can manufacture as much gold as you need to pay for whatever you want to pay for. So gold obviously is not something that you can produce from other elements. So, but alchemy is not something that we use at all today, but we do use some of the glassware. All right, so as we continue on, we'll get into Thompson's model, and then you see Rutherford, Bohrs model, and then you have the modern wave model. We won't get too much into the wave model in this PowerPoint. That actually deals with Schrodinger. And so there's a place on your sheet that you have to fill in for Schrodinger. You're just going to have to go and look up the information for Schrodinger to fill in on that timeline. So let's talk about Dalton. So John Dalton was an English chemist, and he performed a number of experiments that led to the acceptance of the atom. And so he deduced that all elements are composed of atoms. Atoms are indivisible, indestructible particles. Atoms of the same element are exactly alike. Atoms of different elements are different, and compounds are formed by the joining of atoms of two or more elements. Now, these just all make sense. They're just like, this is Dalton's atomic theory. And who has heard of the Dalton's atomic theory before?
I
Y'all-
have.
yeah. So Dalton's atomic theory is an important theory because obviously theories can be changed, but his theory has not changed. Now, the one thing that is different now compared to what he said is that so Democritus said that the atom was a billiard ball. Okay, so Dalton. Now Dalton, I don't know what the heck that was. I'm running out of space here. So the atom, Democritus' atom here is a billiard ball. So Dalton's theory and Dalton's view of the atom is the same. So his model does not change from what Democritus started as. Okay, you can see the picture there, that green sphere. So that represents a billiard ball. Okay, so he is still stating that the atom is indivisible. In fact, it says it right here, and they say that it's indestructible. But this is the key here to this to his model, is that he says they're indivisible. So keep in mind, early 1800s, they didn't have much technology to help them in trying to determine, what exactly the atom was. Now, this theory became one of the foundations of modern chemistry, and I also like to think of Dalton as being the father of chemistry because a lot of the techniques he used is still used today in labs. And so now he published several papers, and those papers are actually papers that are pretty impressive for their time. I don't have any of those papers to show you, but I used to know of a book that you could buy that had a list of all the journal articles that were written by him and these earlier scientists, which I think would be really interesting to read now, considering the fact of how much technology has changed. So, moving on into the later 1800s, we get into what is called J.J. Thompson. J.J. Thompson provided the first hint that the atom is made up of smaller particles. So what's going on now is that we had Democritus, we had Dalton who says that the atom is indivisible. Now we have J.J. Thompson who comes up with this idea that, hey, maybe the atom has smaller particles than what we expected. So he proposed that we have what is called the plum pudding model. The atoms were made up from a positively charged substance with negatively charged electrons scattered about it, like raisins in a plum pudding. And so, now how did he come about this? So what he used was a cathode ray tube experiment. You can see it right here. So that's what we call his experiment that he used. So cathode ray tube, you guys should be old enough to understand. We used to have these big old box TVs, and there would be an old saying, "Turn on the tube." How many have heard of that saying before?
I've heard that before.
For TV.
So, yeah. So in the TV box, there was a tube, a cathode ray tube, and that cathode ray tube, when you turn the electricity on, sometimes you could hear it if you have sensitive enough ears. It would have a ringing sound to it. Now, when I was in college, I experienced this cathode ray tube experiment, not even meaning to. So what Thompson did is that he would take a magnet. So we all know that magnets have a positive end and a negative end, okay? Now this beam of light that you see here is actually a charged substance going through. And so what he did is he brought this magnet close to it. And now in this case here, the negative charge is closest to the tube. And so what he saw happen was the tube deflected away. So it actually pushed the beam of light away from that negative charge. Now he said, well, that was kind of interesting. I'm just paraphrasing. I don't know if he said this way, but This is what I would say. Well, that was interesting. So let me turn the magnet around, put the positive in. Now the beam was attracted towards the magnet, okay? Well, if the atom was just a hard sphere, then the magnet shouldn't affect it at all. So that led to the idea that maybe, just maybe, there's something smaller in the atom. Now, what he couldn't explain is that if there's a negative charge, then where's the positive charge going to be? And that's where we get back to the plum pudding model. That's why he says that the positive charge is throughout the entirety of the atom, and the negative charges are just sprinkled on top because they're going to be attractive towards that big, large positive charge. So obviously that's what he concluded with his model. Now there's some truth to it because the fact is that there are electrons. There is a positive charge, but the question is really, where is the positive charge? He could not explain that. All right. So just a couple things here. All right. So he concludes that the negative charge came from within the atom. A particle smaller than an atom had to exist. So here's where we now have changed from indivisible to divisible. So now we're able to divide the atom into smaller particles. So this next thing right here where it says corpuscles, that's a Jeopardy type word. All right, so if you hear, so we call them electrons now, but back then he called them corpuscles. So since the gas was known to be neutral, having no charge, he reasoned that there must be positively charged particles in the atom, but he could never find them, and that's because of the lack of technology. So again, Democritus, Dalton, and now the plum pudding model. So the atom is starting to change in its structure. So Millikan came in around about the same time, and he produced what is called the oil drop experiment. In fact, Millikan was a grad student when he did this experiment. So what Millikan discovered was the charge to mass ratio, and he used the oil droplet experiment to do this. So oil droplets are basically like hairspray or even air freshener. If you were to spray your air freshener out, it sprays this mist out, and then the mist falls down. And so the mist falls down. Some of them pass through this hole, and inside of this area, you have this source of X-rays that come out as a beam. And when it hits the oil droplets, it causes them to be charged. And if you notice, there's a positive and negative charge. These were connected to a battery. And so when that battery was turned on, it sent a charge in here. And if the oil droplets had any charge, you would see them, the negative ones, travel back up towards. That's where this microscope came into play. He would watch these oil droplets go up and would count them, and based off the charge to mass, he was able to deduce that based off of these observations. So now obviously what you need to know for this part is that that Millikan discovered the charge to mass ratio. He discovered how small the electron was, and basically the charge of it was -1. So he determined the charge on the electron in 1909. So this was just a few years later after the J.J. Thompson produced his article. So now Rutherford is the next scientist in line. In fact, you notice that Millikan and Rutherford published papers in the same year, almost, and so Rutherford came up with what is called the gold-foil experiment. So notice that these scientists have these experiments that they did, which were able to give some indication as to what the atom looks like. Now, so what did Rutherford do? So Rutherford used the gold-foil experiment. Now, we call it the gold-foil experiment because what he did was he took a small sheet of gold, placed it in the middle of this detector, and this big green thing that you see around here is the detector. And he sent alpha particles. All right, so alpha particles are radiation, essentially. Alpha particles are positive charges he sent into the gold foil. And so what happened was is that, so you have a cross section of the gold foil right here. So what happened was these alpha particles would come into the gold foil, and they would come out the other side. Most of them would come out, and some of them would be deflected backwards. Now, what's important to understand is that if we look back at the plum pudding model, the entire thing was positive charge. If you send an alpha particle that is positive charge into the atom that, where in this case was all positive, everything should be deflected backwards. Does that make sense?
Is one of them closer or farther away from the mass spectrometer model?
No, they're all the same distance.
Okay.
So they're all the same distance. But what's important here is that Rutherford is actually demonstrating the fact that most of your particles come straight through. Yes, some are deflected back, but very few of them are sent backwards because most of the atom is made up of empty space. So what Rutherford concludes from this experiment is that the atom has a small, dense, positively charged center that repelled the alpha particles. And I'm going to put this alpha particles here. So remember, the alpha particles are positive charged. And so he called the center of the atom the nucleus. And he states the nucleus is tiny compared to the atom as a whole. So we have Democritus, we have Dalton, we have J.J. Thompson. Now we have Rutherford. So it's definitely changing. It's taking shape. It's getting close to what we see the model as it is. Any questions on that? Do y'all see how the shape is starting to turn into what we see it as today?
Yeah, definitely.
But it's neat because every scientist has their own input as to what is actually happening there. So there's a different point of view. I don't know what kid drew that diagram, but green and red. All right, so the electrons have to be surrounding the nucleus because obviously negative attracts the positive. So each of the atoms have a certain number of electrons and protons, and those electrons are attracted towards the protons, which are found in the nucleus. James Chadwick is the scientist that's responsible for discovering what that's on that paper. So make sure that you look at that paper and notice. Let's see, I don't think I have it up here. I thought I did. So, but either way, that paper tells what James Chadwick is responsible for. Now, Bohrs Model. Everybody has heard of Bohrs Model, I assume. Have y'all heard of it?
Yes.
Yes.
In fact, everyone has seen Bohrs Model. Bohrs Model is a model that was produced by Niels Bohr in 1913, and this was an improvement over what Rutherford came up, because what it does is that it places the electrons into specific energy levels. And so you now have a diagram that looks like this, where the electrons are found in the outer shells in these different orbitals. How many have seen this before? I don't say that I have. Everyone has, because what this is this. How many of you have seen that particular model before, or that drawing?
Have.
Not with
That
the
drawing,
spikes,
yeah. This drawing is a drawing of the Bohr model. Bohr's model is not the best explanation to what the atom structure actually is. It's actually based around Schrodinger's equation, which deals with quantum mechanics and the wave model. We will not get into that today, but what we will see is the fact that we have Bohr's model. So this is the structure. So as we started with Democritus, Dalton, Thompson, then we get into Rutherford. Now we get into Bohr, which gives us the famous drawing that we see in a lot of different videos and TV shows. So, according to Bohr's atomic model, electrons move in definite orbits around the nucleus, much like planets around the sun. These orbits or energy levels are located at certain distances from the nucleus. And so, when we get into the future chapter, we will look at Bohr's model more closely. In the electron cloud, a space in which electrons are likely to be found, electrons whirl about the nucleus billions of times in 1 second. They are not moving around in random patterns. Locations of electrons depend on how much energy the electron has. So when we look at the electron cloud and we look at the different energy levels, the electrons that are found in the outer shell are going to have higher energy than the electrons found on the inner shells. So low energy, high energy. Now the other detail is that the electrons will never be found in between the orbits. They will always be found on the orbits. The plate, so this X right here, this X is called the degenerate zone. Electrons will never be found in the degenerate zone. Any questions on that?
Could you repeat what you just said?
The electrons will never be found in the degenerate zone.
What is a degenerate zone again?
It's a bad place. You don't want to go there.
Okay.
All right, so just to summarize everything we looked at with the different scientists. So this table just lists, that talks about Democritus being indivisible, Dalton's model being indivisible. Thompson provided a first hint at the electron, then Millikan discovered the charge of the electron. Rutherford specifies where the electrons are found, and that the atom does have a nucleus, and then Bohr places the orbits around the nucleus and where the electrons are found. So that's kind of the development of the periodic table, the atom.
Shouldn't Bohr be listed for the nucleus as well in that case?
Well, he didn't discover the nucleus. That was Rutherford. And Rutherford also discovered that the nucleus had to have a positive charge because those alpha particles were reflected back. And so that's not on this table, but it could be. So James Chadwick. Did anybody look up Chadwick yet on that timeline? What did James Chadwick do? What was he responsible for? Who's going to be the first
Did
one
he
to tell?
discover neutron?
Yeah, exactly. He was the person that discovers the neutrons. Yep. So the atomic structure, as we see it today, and this is Bohr's model still, but still we can use this model. It helps to explain. I told you that we'll get into Schrodinger's model later on in the semester. So for right now, I'll let you look up Schrodinger in your own time so you can fill that table in. So there's three parts: the electron, proton, and neutron. So electron and proton are positive and negative charges. So the electron's -1, the proton's +1, and then you have the neutron, which is neutral. Neutron, neutral, should make sense there. And so now the other detail is that we want to know the placement of the protons and neutrons. So the proton and neutron are found in the nucleus, and then the electrons are found on the outside. But what I want you to pay attention to is the fact that the proton's mass and the neutron's mass are the same. Now the electron's mass is much smaller than, it's actually 10,000 times smaller. That sounds like a lot, doesn't it? But when you look at this scale here, so this is -27, and then this is -31. That's a difference of what, 4 decimal places? So that equates to 10,000 times smaller as far as the mass is concerned. So electrons are a whole lot smaller in relation to the proton and neutron. Now, what I want you to try to understand here, and this is where it starts to get a little bit different in the elements, because we know that some elements are radioactive and some elements are not radioactive. So if you go to a gym and you want to lift dumbbells, do you go and get 2 dumbbells that are different weights, or do you get 2 dumbbells of the same weight? What do y'all do?
The same.
It sounds ridiculous to even ask that question, doesn't it?
Yeah.
Yeah, I know. But the problem is that elements don't have that same way of getting the same protons and neutrons. So what happens is that when you have, let's say, 4 protons, and then you have 4 neutrons, and my symbols that I use for this, the electron is represented here, the proton, and then you have a neutron, just so everybody understands that. So you want to make sure that the atom's nucleus, has the same number, because if they don't, then we're going to start having problems. Now, once we start looking at this structure specifically, you're going to find that the elements don't have always the same number of protons and neutrons. So that's like me going to the gym and picking up a 50-pound dumbbell, and then I pick up 100-pound for my other arm. Well, it's going to look ridiculous because it's not going to be very stable. I'm going to be lopsided because one side's heavier than the other side. That's instability. And the more unstable the nucleus is, the more likely it will be to break down. In other words, it'll split apart. It'll lose those differences in the protons and neutrons. That's where radiation comes into play. So when we look at the periodic table, all right, what we have to understand is that once you get to elements 85 and higher, and that I'm talking about the atomic number here. So when you look at the elements, all right, so element 85 and higher, their elements are all radioactive because of the differences between the protons and the neutrons. All right. And so we're going to look at this in just a few minutes. We got about 5 minutes left in the class here. So when you look at this, so you need your periodic table up, by the way. When you look at your periodic table, you're going to see that sodium has an atomic number. So this is atomic number. And then it has a mass number. Now this is the rounded mass number. All right, so this is the mass, mass number. All right. So you are able to determine the electrons, protons, and neutrons from these two numbers. Now, so the way this is drawn out, this is called the nuclear symbol. And the nuclear symbol is oftentimes how we express an isotope or an element in this case. And so all we do with writing the nuclear symbol is you take the mass number, you put it on top, you take the atomic number, you put it on the bottom. Now, what's over here, this usually represents the charge of the element, if it does possess a charge. If it doesn't, then we just put 0 in the top right-hand corner. Now, the way we use this is, so determine the protons, neutrons, and electrons. Well, the protons are always going to be from the atomic number. Okay, so the atomic number gives you your protons. And then the electron, it also will give you the electrons, but do keep in mind that the charge also dictates the electrons, but we're not going to look at that right now. We'll look at that probably on Wednesday. So the mass, so to determine the number of neutrons, what we do is we take the mass number and we subtract it from the atomic number. Okay, so that's the simple way of doing that. Now, to figure out the protons for sodium, you look at the atomic number. There are 11 protons for sodium. And since the charge is 0, there are 11 electrons. Typically, your protons and electrons aren't going to be the same unless it's charged. Now, the neutrons in this example here, we'll take, so 23 minus 11 gives me 12. So for sodium, we have 12 neutrons. Any questions on that? So let's so do y'all have y'all's periodic tables out? If you do, I want you to look up oxygen here. So let's do oxygen. We'll just do a couple while we have a couple minutes left here. So we'll look at oxygen here. So I want to figure out the protons, neutrons, and electrons for oxygen. So to write the nuclear symbol here, I'll have 16, and I'll have 8, and then the upper right-hand corner is 0. So to figure out the protons, I look at the atomic number. The atomic number for oxygen is 8. So I have 8 protons, and then the charge is 0. So I have 8 electrons. Now to figure out the neutrons, I do 16 minus 8, which gives me 8 neutrons. So again, 16 minus 8 gives me that value for the neutrons. Does everybody understand that?
Yes.
All right. So we got another minute. Let's do one more here. Let's do uranium. Let's see here. I gotta find uranium's mass number. I think the top number is 92. Yep. So uranium.
Yes, 92.
Yep. All right. So uranium is U. That's a terrible U. So U 92, and then the bottom number is 238. 238. So the protons, there are 92 protons, and then there are 92 electrons. To figure out the neutrons, we got to do 238 minus 92, which gives me 146 neutrons. What I want you to pay attention to is the fact that you have 146 neutrons and 92 protons. That's going back to the example we talked about earlier with me picking up a 100-pound dumbbell and a 50-pound dumbbell. These are not equal to each other. These are very far apart. This element is very unstable, and it breaks down very quickly because of that. And in that doing so, it creates what is called radiation, and that's because of this instability in the nucleus of the atom.